Your propane tank is a subscription you never agreed to sign. You can smell it before the stove even lights. That faint chemical bite in the cold air, the hiss of pressurized gas bleeding into the burner. A full 20-pound cylinder lasts a serious cook maybe 2 weeks of daily use. 2 weeks, and then you're driving to the exchange rack, handing over cash, and starting the clock again. Every single time. The Vikings had a different arrangement. They weren't buying anything from anyone. They cooked at temperatures that rival a modern gas range using nothing but forest scraps and the physics of moving air. And the device that made it possible is so well engineered that modern thermodynamic science had to spend decades reverse engineering why it works so well. You have been paying for fire. You don't have to. There's a design principle baked into every propane appliance you own, and it was never built in your favor. Propane is sold as convenience. But what it actually delivers is dependency. The U.S. Energy Information Administration tracks propane price volatility across every major supply disruption. Hurricanes, refinery shutdowns, hard winters. And the pattern is consistent. Residential propane prices routinely spike 40 to 70% within days of a supply interruption, with no meaningful warning and no consumer recourse. The tank in your yard doesn't protect you from that. It just delays it by 2 weeks. You're not insulated from the system. You're just further back in the queue. That is the whole product. The Vikings called their cooking hearths eldsteder, fireplaces literally, and the ones excavated at Borg in northern Norway, dating to roughly 800 CE, show something modern fire engineers immediately recognize: a channeled combustion chamber that forces air up through a restricted throat before the flame reaches the cooking surface. They weren't doing this by accident. They were exploiting a principle of physics that took Europe another 1,000 years to formalize. That principle is the reason a rocket stove produces more heat from a fistful of sticks than a campfire produces from half a log. The science is called induced draft, and it works like this. When air is forced through a narrow passage, it accelerates. Faster-moving air carries more oxygen molecules per second into the combustion zone. At more oxygen per second means the fuel burns hotter and more completely, releasing more of its stored energy as heat rather than as smoke. The narrow vertical channel inside a rocket stove, called the riser, creates a self-reinforcing loop. Heat rises, drawing in fresh cold air at the base, which feeds more oxygen to the fire, which creates more heat, which pulls in more air. And combustion engineers call this a thermosiphon effect. The fire is essentially pumping its own oxygen supply the same way a beating heart pumps blood, continuously and without external input. The riser in a well-built rocket stove reaches internal temperatures above 1,000 degrees Celsius, hot enough that unburned carbon particles, which are what smoke actually is, are reignited and consumed before they ever leave the chamber. Think of it this way. A standard open campfire is like trying to breathe through a wet wool sweater. Half the oxygen never reaches your lungs. The effort is enormous, and most of the energy is wasted. A rocket stove's combustion chamber is a clean, dry snorkel. Every breath is full, every molecule of fuel reaches the fire, and almost nothing escapes unused. That is not a metaphor for efficiency. It is the mechanism of it. Here is the part the propane industry would rather you never learn about fire. Wood that burns at high enough temperatures undergoes a secondary chemical process called gasification. The heat drives off volatile gases trapped inside the wood fibers themselves, gases rich in hydrogen and carbon monoxide, both of which are themselves combustible fuels. In a standard campfire or an ordinary wood stove, these gases drift up and away unburned, taking a significant portion of the wood's total energy with them as smoke and soot. In a rocket stove operating at full temperature, those gases are caught in sparsosaurus, the combustion zone, and burned as a secondary fuel source within the same chamber. The U.S. Department of Energy has published research showing that advanced combustion designs, including rocket principle stoves, achieve thermal efficiencies of 35 to 45%, compared to 10 to 15% for an open fire and roughly 30% for a conventional propane burner. You are not just burning wood, you are burning everything wood contains. Before you build, gather your materials. The core construction uses fire brick. Standard 9-inch by 4.5-inch by 2.5-inch splits work reliably and are available at most masonry suppliers for under $2 each. You will need approximately 25 to 30 bricks for a functional ground-level unit. You also need a short length of 6-inch diameter steel pipe for the riser. 12 inches is the minimum effective height. though 16 inches produces noticeably stronger draft. A flat steel plate or a salvaged cast iron pan grate serves as the cook surface. High-temperature wood stove mortar is optional for a permanent build. For a field-portable version, dry stacking the bricks is entirely achievable and allows the stove to be disassembled and transported. Begin by laying your base course of bricks flat on level ground, forming an L shape. One arm 3 bricks long becomes the horizontal fuel feed, and the short vertical section, 2 bricks wide, anchors the riser. This L configuration is not aesthetic. It is functional. The horizontal arm is where you slide your fuel in from the side, controlling burn rate by how far you push the wood forward. Leave a clear gap of roughly 3 inches beneath the horizontal arm using 2 bricks laid on edge as legs. This is the primary air intake, and blocking it is the single most common build mistake. As you stack the riser section, work carefully. Fire brick is dense, and the edges chip if dropped. So keep your courses level and stagger the joints just as you would in any brickwork, so no vertical crack runs the full height of the riser wall. For steps 4 through 6, the crest-kid the cap the top of the riser with your steel pipe section, setting it so it extends at least 4 inches above the top brick course. This is where the thermosiphon effect is strongest and where secondary combustion completes. Your cook surface, whether a steel plate or grate, sits directly over the pipe mouth. The cooking zone is intense. Surface temperatures directly above the riser mouth exceed 450 degrees Celsius at full burn, so use long-handled cookware and position your hands to the side, never directly above the flame path. For your first fire, use small-diameter dry kindling no thicker than your thumb. Pencil-width sticks are ideal, and feed them horizontally into the fuel arm one at a time. Within 3 to 4 minutes of lighting, you will feel the stove reach operating temperature as the draft establishes itself. At that point, the fire becomes nearly self-managing. The performance data is not theoretical. Independent burn tests conducted by the Propane Research Center, a US-based sustainable cooking technology institute, documented rocket stove designs boiling 1 liter of water in under 4 minutes using less than 75 grams of dry wood. By Chappus, a standard propane burner on a camping stove uses roughly 8 grams of propane to achieve the same task. The wood weighs more per task, but it costs nothing and grows back. At peak operation, riser temperatures inside a well-built unit sustain above 650 degrees Celsius continuously, hot enough to cook, bake, boil, and sterilize water without variation. The cost comparison is not close. A 20-pound propane cylinder exchange currently runs between $20 and $28 at retail in most US markets, and you go through it in 2 weeks of regular cooking. The fire brick and pipe for a rocket stove build cost between $35 and $55 total. A one-time expenditure. After the first 2 weeks, your fuel is whatever dry wood you can gather, scavenge, or cut. Pallets, branches, scrap lumber, dead hedgerows. The fuel is everywhere. The propane is at the mercy of a distribution system that does not know your name and does not care about your dinner. The Propane Research Center's own global field data, drawn from deployment of rocket principle stoves across more than 40 countries, consistently shows 50 to 75% reductions in fuel consumption compared to traditional open fires and conventional stoves. This is not a fringe experiment. It is a documented, repeatable, internationally validated result. Millions of households on every inhabited continent already cook this way. The knowledge is not new. The decision to use it is. Also, the supply chain that fills your tank runs through refineries, rail lines, and distribution hubs, every single one of them a single point of failure. One hard winter, one logistics breakdown, one price spike decided in a boardroom you will never enter, and your ability to cook hot food becomes someone else's variable. You either own your fire or you rent it. Those are the only 2 options on the table. Your move. If this build belongs in your prep, save this now and share it with one person who still thinks propane is a plan.